So what I got here is a molarity versus time graph. Molarity is in moles per liter, that's its units. Time, I put in milliseconds. Reactions tend to happen pretty quick, so I thought milliseconds would be good. And what we're going to do is we're going to put 4 lines on this graph that relate to the chemical reaction we did in this lab. So it says in the target, I can make a graph of molarity versus time for our lab reaction showing each of the 4 species. And the 4 species that this is referring to are, I'm going to use different colors here. Let's just say green is Li2SO4. I know that that's a hydrate. It's got a .H2O. I'm just going to leave that off for simplicity. Let's say orange is BaCl2. Once again, I know that's a hydrate, but for simplicity, we're going to leave it off. Let's let the red be LiCl. I know there are 2 of those that come out of the equation. I'm not really worried about balancing anything up here. I just want the species. The species is lithium chloride, and then barium sulfate, BaSO4. And we know from, remember that? And from the same reaction you have in your survival guide, there is that 5th species, which is water. But I'm leaving that off because that water is only there because it's carried inside these wet crystals and plays no role in the actual reaction itself. It's just we have to account for its mass because we weighed wet crystals. So not even worried about that water. These are the 4 species that matter. Okay, so let's talk about the barium chloride. Let's start with the barium chloride. Barium chloride is an ingredient, it's a reactant, and more specifically, it is the limiting reactant. Remember, the limiting reactant is the one that runs out first. And once you, deep concept here, once you run out of an ingredient, the entire process stops. So we, in our lab, made barium chloride the limiting reactant. And here's what that looks like on the graph. Okay, so just before the reaction started, barium chloride had some sort of high value. We had dissolved it into water, and it was as concentrated as it was going to get. We don't care about the actual molarity. We just know that it's an ingredient, and ingredients start high, and they get used up as time goes on. So we're just going to stick barium chloride up there somewhere, some sort of high value, and as the reaction proceeds, ingredients get used up, so those ingredient particles leave, and because they're being converted into something else, so their molarity, the number of moles of those ingredient particles, drops over time. And so the molarity being the number of particles per liter, is going to go down. So the molarity drops and drops and drops and drops and drops, and eventually hits 0. Let's just say right there, hits 0 molarity. It hits 0 molarity because it's the limiter, and that's the definition of a limiter. The limiter is the ingredient that runs out first. Runs out means 0 is left. So this is a molarity versus time graph for that one species. Starts high because it's an ingredient and gets used up over time and ends up completely running out. All right. Now, lithium sulfate is also an ingredient. It is not the limiter though. We call that the ingredient in excess. And the ingredient that is in excess, the reactant that is in excess, does not run out first. And since it doesn't run out, there is a lot left over. There is some left over. That is what in excess means. It means that you have more than enough. It means that when the limiter runs out, you still have some left over. That is what in excess means. And since lithium sulfate was in excess, we put it in excess by 5%. It means that since it's an ingredient, it's going to start high up there. Let's just put it right here. And as time goes on, its value, its molarity is going to go down because it gets used up. So the number of lithium sulfate particles in solution is dropping every second. And so it's going to go down, and right here, it levels off. It does not reach zero. Okay, this is a key area of this graph. You see, I had said that the entire reaction stops once the limiter runs out. Once this goes to zero, there's no way for lithium sulfate and barium chloride to react anymore because there's no more barium chloride. What you're going to have is the reaction. This is going to stop going down because it's not getting used up anymore. It's just going to level off, and you're going to have a certain small but existent molarity above zero, which means this represents, this distance here represents the amount that is still there that never got used up. That's why it's in excess. You have an excess amount of it. If it wasn't in excess, it would have all got used up. But we purposely put that in excess in this lab. So this is what lithium sulfate looks like. So here you have, this is what a limiter looks like, the barium chloride. This is what something in excess looks like. There. All right, so that takes care of the molarity versus time graph for that species and that species. Let's talk about lithium chloride. What does it do? Lithium chloride is a product, and at the beginning of the reaction, just before the two ingredients meet, you have zero molarity. You don't have any. You haven't made any products yet. So if you haven't made any products yet, there are no product particles, and therefore there is no moles of product in the liter of solution that we're working with. But as time goes on, you're going to start making this product. And so its molarity is going to go up. So it goes up and up and up and up, and eventually right here, it stops and levels off. So why? Well, notice, it stops being made when the limiter runs out. That's what a limiter does. When it's called the limiter. When the limiter runs out, the entire process stops. You have used up a key ingredient, and therefore you can't make products anymore. Since lithium chloride is a product, you can't make any more of it. Lithium sulfate and barium chloride are not reacting together anymore because there is no more barium chloride. And therefore, you cannot make any more lithium chloride. Notice the relationship here. At that point, when that runs out, this stops getting consumed and this stops getting made. The molarity is constant, it doesn't change. The same number of particles exist in solution here as here as here as here, because you're not making any more, you're not using up any more. Using up any more of that, not making any more of that. All right, so this is what the lithium chloride looks like. So that takes care of that one. Okay, so what about the barium sulfate? Now the barium sulfate's a trick question. Okay, barium sulfate is our precipitate. Precipitates don't dissolve in water. So it would not have a molarity. As soon as barium sulfate forms, it just comes out of solution and falls down to the bottom of the beaker and builds up. So because it's a product, you would start at 0, but because every time a barium sulfate forms, it falls out of the solution and is not dissolved into the solution, it remains at 0 the whole time. Molarity is a measure of dissolving and how many particles have been dissolved into solution. Since barium sulfate doesn't dissolve, it doesn't have a molarity. Therefore, it's just going to remain 0 all the way through the entire process. It's a trick because it really doesn't have a place on this graph. All right, there. That's how you do target 6-5. What you would do on the test is you'd be given the axes of the graph, and you're going to sketch the curves, and you're going to explain those curves. You're going to say, this is barium chloride, this is Y, it's the limiter. This is the lithium sulfate, and it is in excess. This is the lithium chloride product. It stays dissolved, it's aqueous, it stays dissolved. And then barium sulfate's not on there, or it's equivalent to the bottom line because it doesn't have a molarity. It really doesn't have a place on a molarity versus time graph. So we're just going to say it's on the bottom. All right, there. That's what you do on the test. Okay, see you later.